All right, let's take a look at classifying chemical changes and predicting products. In the warm-up, we have different types of reactions. We have a synthesis or combination reaction where I have two reactants coming together as one product. Decomposition is the reverse of a synthesis reaction where I have one reactant decomposing or breaking apart into two different substances. Single replacement is where I have an element combining with a compound, and then I produce a new element in a new compound. Double replacement is where I have two compounds combining, and then parts of those compounds transfer or switch with each other, and I get two new compounds. In neutralization reaction, I have an acid combining with a base. This would be something beginning with hydrogen. Base would contain hydroxide. You're going to produce a salt, which is an ionic compound, and water. Combustion reactions are when you have a hydrocarbon or an organic compound, which is composed of mainly carbons and hydrogens, and it's going to combine with pure oxygen to make carbon dioxide and water. Now, based upon these reaction types, we want to use that table to classify each of the major reaction types listed underneath. So if you take a look at number 1, we have sodium combining with water. So sodium is an element, water is a compound, and then that means I am looking here at this single replacement reaction. So I'm going to abbreviate that with an SR. For number 2, I have lithium oxide combining with water to make lithium hydroxide. So I'm bringing together two substances, so I have two reactants, and I'm making one product. So this would be a synthesis or combination reaction. So I'm going to abbreviate that with an S. Number 3, I have a compound that's made of carbons and hydrogens. This would be a hydrocarbon or an organic compound, combining with pure oxygen to make carbon dioxide and water. So this would be a combustion reaction, and I'm going to abbreviate that with a C. Number 4, HCl. This is hydrochloric acid combining with strontium hydroxide, which is a base, making strontium chloride, which is a salt, and water. So this would be a neutralization reaction, which I'm going to abbreviate with an N. Number 5, this is aluminum bromide decomposing into aluminum and bromine. So I have one reactant decomposing into two different substances. So this is decomposition, and I'm going to abbreviate that with a D. Now, there are obviously different types of reactions, and we're going to take a look at the details of each one, and I'm going to start with a synthesis reaction here. And synthesis reactions are usually releasing energy in the form of heat or light. So that means that synthesis reactions are exothermic, and they sometimes require a really small amount of startup energy to begin. This startup energy is known as activation energy. So if you're going to light and burn a match, activation energy is required for both of those processes. So striking a match against a rough surface is going to provide activation energy for this exothermic reaction between red phosphorus that's on this match head and the oxygen that's in the air. And the product of this match lighting reaction is a white gaseous oxide of phosphorus. And this reaction is given to you on the next page, where they're showing you that energy is being released as a product. So that means this is an exothermic reaction. And the activation energy is provided by the exothermic reaction, or the heat, for a second reaction that involves the combustion of wood or paper of the match stick. And combustion is also an exothermic reaction. So synthesis reactions are going to generally involve the combination of two elements to form a binary compound. These are both ionic compounds. Here is one example. Barium combines with chlorine to make barium chloride. So these are two elements forming a simple binary compound. Here I have tin combining with oxygen to make tin 2 oxide. And notice here that this is just tin solid. There is no Roman numeral associated with that until it gets into this compound. It is tin 2 oxide. And Non-metal oxides, when they combine with water, they will always produce an acid. So down here, when you have SO3, which is a non-metal oxide, because sulfur is a non-metal, when it combines with water, here is your acid, sulfuric acid, that you are producing. Now, when we have a metal oxide reacting with water, you're going to form a base, and this example is here. Here is your metal oxide, potassium oxide, combining with water to form potassium hydroxide, which is your base. One other example is when a metal oxide reacts with a non-metal oxide to produce a complex or ternary salt. That is this example down here. Here is your calcium oxide reacting with carbon dioxide, which is a non-metal oxide, to produce a ternary salt because it's made of three things. That's calcium carbonate. Let's talk about decomposition reactions. Decomposition reactions are when you're breaking things down. You have one reactant. It's the opposite of a synthesis reaction, which means this is going to be endothermic, so this will absorb energy. And you're absorbing energy to break bonds, typically, right? So in this case, decomposition reactions are commonly used in the mining industry to separate metals from their ores. And you can see that as an example down here in this figure. We produce aluminum metal and oxygen gas from melted bauxite ore. Let's go to the next page. Here they have summarized some decomposition reactions for you. And remember, these are the reverse of the synthesis reactions that we just talked about. An acid decomposition reaction, forming water and a nonmetal oxide. A base decomposition reaction to form a metal oxide and water. A ternary salt, this would be a ternary salt decomposing to form a metal oxide and a nonmetal oxide, okay? All of these decomposition and synthesis reactions are summarized in this table for you here. Let's talk about combustion reactions. Combustion reactions are when you have a hydrocarbon or a carbohydrate reacting with oxygen in the air to produce carbon dioxide and water. These are exothermic. They release a lot of energy in the form of heat, sometimes light, even sound. And the water that's released is typically going to be released as water vapor. The combustion of hydrocarbons like propane or gasoline or natural gas provides most of the energy in our houses. And the following combustion of octane, this is octane in gasoline. This provides the energy to move our vehicles. And slow combustion is sometimes referred to as oxidation. This happens in the cells of our body to produce energy. This is one of the common examples of that type of reaction where you have glucose reacting with oxygen to produce carbon dioxide and water. So let's take a look at the quick check on the next page. This says balance the following reactions and classify them as synthesis, decomposition, or combustion. Here I'm bringing two different substances together to make one product. So this would be a synthesis reaction. For number 2, we have a hydrocarbon reacting with oxygen to form carbon dioxide and water. So this is combustion. For number 3, we have carbonic acid decomposing into water and carbon dioxide. So this would be decomposition. And if you were to balance this, the coefficients on number 1 would be 1, 3, 2. For number 2, it would be 1, 2, 1, 2. And then this is already balanced for number 3. Those coefficients are all 1s. Let's take a look at a sample problem here. Here we want to predict the products of 3 different reactions. So for this, we have a hydrocarbon for number 1. This is methanol reacting with oxygen. So this is a combustion reaction, so it's going to produce carbon dioxide and water. And if you were to balance it, your coefficients would be 2, 3, 2, 4. For number 2, we have a non-metal oxide reacting with water. When you have a non-metal oxide reacting with water, you're going to produce an acid. And the acid that you're going to produce is H3BO3. Now, I would not expect you to know how to predict the acid that is being formed in this case. BO3 -1 is -3 is borate, and borate, when it combines with hydrogen, is H3BO3, so this is boric acid. And if I were to ask you to balance this, your coefficients would be 1, 3, and 2. For number 3, this is a decomposition reaction, and this is a base because it has a hydroxide in it. And when bases decompose, they form a metal oxide and water. The metal here is scandium. So scandium has a +2 charge, or actually in this case, scandium has a +3 charge because that is the charge that you would calculate on the metal. So this would be Sc +3, O -2, you would cross it, you would get Sc2O3 for your metal oxide, and then you're also forming water, which is H2O. And to balance it, this would be a 2 and a 1 and a 3, okay? Now, let's take a look at the practice problems on the next page. Here we want to classify the equations, then determine the products, and write a balanced formula for each of the following. So for number 1, we've got a metal oxide. Metal oxides, that's going to decompose, so this is decomposition. And it's going to decompose into its 2 elements, which are iron and oxygen. If I'm going to balance this, I'm going to require a 2 in front of Fe2O3, a 3 in front of O2 to balance the oxygen, and then you have 4 irons. For number 2, this is a combustion reaction. This is a hydrocarbon reacting with oxygen. And that means you're going to produce carbon dioxide and water. And when you're balancing this, you're going to end up, you can pause the video, balance it on your own, and see if you end up getting 2968. For number 3, this is a metal oxide combining with water, so that means you're going to form a base. A base is going to be a cation with an anion. Silver is going to combine with hydroxide. Silver is +1, hydroxide is -1. And then to balance this, you're going to need a 2 in front of AgOH. And this is a synthesis reaction, and if you look back at the table for the summary of different types of synthesis reactions, that's where you're going to find the metal oxide plus water is giving you a base. For number 4, this is lead 4 hydroxide. This is a base that is decomposing. And when you have a base that's decomposing, you're going to form a metal oxide and water. So So your metal oxide is going to be lead 4 and O negative 2. The numbers in the charges can be simplified to a +2 and a -1. So you're going to cross those and get PbO2. To balance it, you just need a 2 in front of H2O. Okay, let's talk about single replacement reactions. Single replacement reactions are also known as single displacement reactions. And this is where you're going to have a free, uncombined element that's going to kick out an element in a compound. So it's going to take its place, and metals replace metals, and non-metals replace non-metals. So the more active metal can also replace hydrogen, and you're going to produce hydrogen gas. They have outlined these 3 different types of replacement reactions for you here. Metal replacement is where you have a metal here in this is your elemental form, your free uncombined metal. And it is going to, I'm going to call it metal 1. It is going to replace metal 2. So when these switch places, you're going to kick out copper alone, and then potassium will combine with nitrate and give you potassium nitrate. Sometimes it's easier to write these out in words. For instance, if you write this out as potassium combining with copper 2 nitrate, the potassium and the copper are going to switch places. And that's how you get the potassium nitrate and the copper. Now, when the copper is alone, it's not going to have a Roman numeral in its name. It's not going to have a charge on it. It's just going to be a solid metal. That's why you don't see any charge here. That Roman numeral is only important when it's in a compound. Generally speaking, if you have a metal, a transition metal, and you don't know what the charge is going to be on that transition metal when you put it in a compound, it is generally a +2 or a Roman numeral 2. Okay? For the hydrogen replacement, when you have a metal alone, it can replace hydrogen in water. If you rewrite water as hydrogen hydroxide, the sodium and the hydrogen will switch places. You'll end up with sodium hydroxide, because this sodium will combine with this hydroxide, and you'll kick out hydrogen gas. You can also write this out in words as sodium followed by hydrogen hydroxide. And the hydrogen and the sodium switch places, and that's how you get your sodium hydroxide and your hydrogen gas. Okay? Now, for non-metal replacement, if your free uncombined element is a non-metal, it will usually be a halogen, which is from group 17. This non-metal will replace the non-metal. I'll call this non-metal 1. This is non-metal 2. This non-metal that is free will replace the non-metal in the compound, and when they switch, you'll get sodium bromide and iodine. Again, you can write this out in words if it's easier for you to predict what the products are. Now, in order to figure out whether a single replacement reaction will happen or not, we have to look at the chemical reactivity of the elements that are being replaced. The more reactive element will always kick off a less reactive one. So if you look here at this table, here you'll notice that the metals are on the left, the halogens are on the right, and the more reactive ones are at the top. So fluorine is more reactive than chlorine. Chlorine is more reactive than bromine. Bromine is more reactive than iodine. So when it's a non-metal replacement, you look here. And if the nonmetal that is free is higher on this list or more active than the one in the compound, then it will replace it. Over here on the left side, these are your metals. You would look here for metal replacement or hydrogen replacement. You'll notice that hydrogen is capitalized and starred down here. That's because hydrogen can be displaced from acids by metals that are above it in the series. So lithium would be the more reactive or the most reactive metal on this list. It can replace potassium or calcium or sodium or hydrogen or anything underneath it. I'd like you to add in between lithium and potassium Rb for rubidium, and then I'd like you to also have a CS, cesium above Rb. That's just for the homework later on. So the ones that are down here, these are less reactive on both sides. Okay, so let's go ahead and take a look at the quick check. Just underneath. So here we're going to use the series of chemical reactivity in the table above to figure out if these single replacement reactions will actually proceed. If they do not proceed, you simply write no reaction. And then we're going to predict the products for the ones that proceed. So here I have sodium alone, so this is a metal. So this is going to be a metal replacement. And I want to see if the sodium is more reactive than the metal in the compound, which is aluminum. So yes, sodium is more reactive than aluminum. So that means that the sodium will replace it. So these two will switch. You'll kick out aluminum alone, and then you'll have sodium combining with chlorine, and that will make sodium chloride. Sodium has a +1 charge, chlorine has a -1 charge. They cancel, that's how you get NaCl. I'm going to put a 3 in front of NaCl to balance the chlorine, and a 3 in front of sodium. Okay? Number 2, I have copper metal alone. That means I'm comparing it with potassium. Is copper metal more reactive than potassium? No, it's not. Copper is less reactive than potassium. So that means that this reaction will not take place. So you would simply write no reaction. And this was possibly a metal replacement reaction. So that's why I'm indicating it over here. Okay? Number 3, F2 is a nonmetal, it's a halogen. So that means I'm going to compare it with the nonmetal in the compound, with it, which is iodine. So look at the right-hand side of the activity series up above. Is F2 more reactive than iodine? Yes, it is. So we're going to make a note, F2 is more reactive than iodine. So that means the F2 will replace the iodine. So when the F2 and the I switch places, I kick out iodine alone, which is diatomic, so that's why I write I2. Then the lithium combines with the fluorine to give me lithium fluoride. Lithium has a +1 charge, fluorine has a -1 charge, they cancel. I need to put a 2 in front of LiF to balance it, and I need to put a 2 in front of LiI to balance it. So this was a non-metal replacement. Number 4, I have calcium alone, which is a metal, and then I have hydrogen hydroxide, which is water. So I'm looking to see, since hydrogen, I'm going to make a note, Hydrogen is a cation. Metals form positive charges as well. They form cations too. So those are the two that you would look at to switch places, okay? So this is going to be a hydrogen replacement. Hydrogen can be replaced in acid, and it can be replaced in water, okay? So is the metal that's alone more active than hydrogen on the list? And the answer is yes. Calcium is more reactive. It is further up on the top, towards the top, than H2. So that means that the calcium and the hydrogen will switch places. You'll kick out hydrogen, which is diatomic, and you're going to form calcium hydroxide. You have to cross the charges. Calcium has a +2 charge. Hydroxide is a -1. And then you need to put a coefficient of 2 in front of HOH to balance it. Now, if you want to write these out in words as sodium plus aluminum chloride, and then switch the words sodium and aluminum to get aluminum plus sodium chloride, that is totally acceptable. I would totally recommend that. Now, let's talk about double replacement reactions. All right, double replacement reactions are when you have ionic compounds, which are made up of a cation followed by an anion, and they are going to have the ions trading places. So the two cations, which are listed first in each compound, will trade places. Now there are 3 different categories of double replacement reactions. There are, this pen is done, let me get a new pen. There are precipitation reactions, neutralization reactions, and gas formation reactions. So those are your 3 categories. And in precipitation reactions, you're going to have 2 new salts formed, and one of them will not be very soluble. It will have low solubility, which means you're going to form a solid. It will likely look cloudy. So one of your products will have a little S in parentheses after it as its state of matter. We're going to talk more about solubility in a later chapter, but for now, what you should know is that compounds containing the alkali metal ions, which are group 1 ions, and nitrate ions are always soluble. That means they will have an AQ after them because they will be soluble in water. Anything that has low solubility will have a little S after it and will be a solid. Okay, this is on the product side. Here you'll notice I have a precipitation reaction here. Sodium chloride solution combines with sodium nitrate solution. The cations, the sodium and the silver ions, switch places. That's how I formed silver chloride and sodium nitrate. Here is my precipitate here, the silver chloride. Nitrates are soluble in water, which is why it has an AQ after it. Neutralization reactions occur between an acid and a base, and the products are always a salt, which is an ionic compound, and water. And neutralization reactions have a little bit of heat that is released. That's why you see heat written here as a product in this neutralization reaction. So here is sulfuric acid combining with potassium hydroxide, which is my base, forming potassium sulfate, which is my salt or my ionic compound, and water, and then a little bit of heat is released. A few products of double replacement reactions are not going to be very stable, and they're going to spontaneously decompose. So what you should know is which ones are not stable. The first one is carbonic acid. Carbonic acid is H2CO3. it will decompose immediately to form carbon dioxide and water. So you want to replace H2CO3 when you see it as a product with carbon dioxide and water, which they've done in this example here. Here we have potassium carbonate combining with hydrochloric acid. The hydrogen and the potassium switch places. That's how you form potassium chloride and carbonic acid. This was H2CO3. They didn't write it that way because it decomposes immediately to carbon dioxide and water. So that's this example here. Now, the other one that is not very stable is ammonium hydroxide. Ammonium hydroxide is NH4OH. It immediately decomposes to ammonia gas and water, which is down here. Okay, so just keep that in mind. If you see NH4OH on the product side, in anything, you want to immediately get rid of it and just write H2O and NH3 in its place. Let's take a look at a sample problem on the next page. Here we are predicting the products of the following replacement reactions. So I have bromine combining with potassium iodide. Bromine is a nonmetal. This is a single replacement reaction, so the bromine and the iodine are the ones that are going to switch places. When they switch places, you're going to end up forming potassium. You can't really see that at all, actually, so let me get a different marker. All right, is that any better? Not much better. Okay, let's try something else then. There we go. That's better. Okay, bromine is a nonmetal. It's a halogen. It will switch with the iodine. So when these switch places, you're going to end up forming potassium bromide and iodine. So that's why you get KBr, because this is a +1, this is a -1. Iodine is a diatomic element, which is why you have I2. Then if you're going to balance it, you're going to put a 2 in front of Ki and a 2 in front of KBr. For number 2, here I have lithium sulfite and calcium nitrate. So the lithium and the calcium will switch places because the cations switch places, and you form calcium sulfite and lithium nitrate. And that's getting kind of hard to see as well. Now we cross charges. Calcium is Ca+2, sulfite is SO3 -2. Those cancel. I get CaSO3. Lithium is Li+1. Nitrate is NO3 -1. Those cancel, and you get LiNO3. You're going to need to put a 2 in front of LiNO3 to balance the nitrate and the lithium, and then your calcium and your sulfite are already balanced. For number 3, you've got sodium carbonate and hydrobromic acid. So I'm going to write this as sodium carbonate. Instead of writing this as hydrobromic acid, do this with all the acids. Write it as hydrogen and then whatever ion is attached to it. In this case, it's bromide. Write the acids incorrectly, okay? Because it's easier for you to predict what the products are. The sodium and the hydrogen switch places because those are cations. Cations switch places. You're going to form hydrogen carbonate and sodium bromide. Okay? Hydrogen carbonate is going to be H plus 1, CO3 minus 2, that's H2CO3. Now, that's carbonic acid. We just talked about how carbonic acid is really unstable, so we don't want to write H2CO3 as a product. I want to replace this with H2O and CO2, okay? Sodium bromide is NaBr. Now, for balancing purposes, I need to put a 2 in front of HBr and a 2 in front of NaBr, and then we are balanced. Now, let's go on to the last set of practice problems here. We want to classify these equations, and then we want to determine the products, and we want to balance them. Let me make this a little bit bigger. For number 1, we have an acid combining with a base. So this would be a neutralization reaction. For number 2, zinc is combining with silver chlorate. That's an element combining with a compound. This is a single replacement reaction. Since zinc is a metal, it's actually a metal replacement. For number 3, I have ammonium sulfide combining with cesium hydroxide. That's a double replacement. For number 4, I have chlorine combining with lithium sulfide. That's a single replacement reaction, and chlorine is a non-metal, so this is a non-metal replacement. Okay, now for number 1, I'm going to write this not as hydrochloric acid, but as hydrogen chloride. And this is combining with iron 3 hydroxide. So the hydrogen and the iron 3 are going to switch places. And that's how I get iron 3 chloride plus hydrogen hydroxide, which is just water. So I'm going to cross charges. That's going to give me FeCl3 and HOH. And then to balance it, I'm going to need a 3 in front of HCl to balance the chlorine, and a 3 in front of HOH to balance the hydrogen with the hydroxide. Let's take a look at number 2. Here I have zinc combining with silver chlorate. Since this is a single replacement reaction, you need to look and see if the zinc is going to be more active than the silver in the activity series. And it is, so that means it will replace silver in the compound, and you're going to form zinc chlorate plus silver metal. If I cross charges, I get ZnClO3 plus Ag. 2 chlorates, we're going to put a 2 in front of AgClO3 and a 2 in front of Ag. And that's your balanced reaction. For number 3, we've got ammonium sulfide combining with cesium hydroxide. The cation in each will switch places, and I will get cesium sulfide and ammonium hydroxide. One of the common questions I get is, does it matter the order that I write the products in? No, what matters is if you're writing an ionic compound, the cation has to go first and the anion has to go second. But it doesn't matter if you wrote ammonium hydroxide in front of cesium sulfide, and number two, it doesn't matter if you wrote silver first and then zinc chlorate second. You're going to cross charges here. You're going to get CS2S plus ammonium hydroxide is NH4OH. Now, ammonium hydroxide is on the previous page. It decomposes because it's not stable into ammonia gas and water. So that means that we have to get rid of this NH4OH and we have to replace it with NH3 and H2O. And then to balance this, we're going to need to put a 2 in front of NH3 to balance my nitrogen. And then I need a 2 in front of cesium hydroxide to balance my cesium, and a 2 in front of H2O. Let's look at the last one. Chlorine plus lithium sulfide. Now for this one, you would not know that sulfur is not a halogen. Chlorine, being a nonmetal, should trade places with sulfur because it's also a nonmetal, but since this is single replacement, if you look at the halogen activity series, you can't necessarily predict that it would replace the sulfur, but I'm going to go ahead and give you these products anyway. You're going to end up kicking out the sulfur and forming lithium chloride. And I would never give you something like this on a test or a quiz where you couldn't predict it. Sulfur, the stable form of pure sulfur is going to be S subscript 8. Lithium chloride is LiCl. Again, you wouldn't know this. And then I'm going to balance this by putting an 8 in front of Li2S, a 16 in front of LiCl, and an 8 in front of Cl2.